Thank you very much. Many thanks for this invitation. I'm very happy to be here to talk in this school. So we'll be giving 3 lectures, and I think I will divide the topics into these 3 parts. The first lecture will be about sheaves and cohomology. Second lecture will be about varieties and bundles. And the third lecture, if there will be any time at all left by the previous 2 topics, will be about modular spaces, by which I mean modular spaces of bundles, of stable or semi-stable bundles. Let's say modular spaces of bundles. Let me also suggest some references from the beginning. There are some standard. Well, first I will say something more general. One can do algebraic geometry basically using any field as a field of coefficients. In particular, should one define what algebraic geometry is, of course, it's not easy, but one could say it is the study of the spaces of solutions to algebraic equations. And you can do this on any field, so with taking coefficients in any field. On the other hand, I believe that what we are most interested in is the case of the complex numbers. And that makes an introduction to algebraic geometry easier, because we can, at least at the beginning, we can we can enter algebraic geometry coming from complex differential geometry, which is perhaps more familiar. From this viewpoint, the book which basically follows this approach is the standard book by Griffiths and Harris. Which is called Principles of Algebraic Geometry. While a book which is really deep into the true algebraic setting is Hartshorne. The title is Algebraic Geometry. And very modestly, I can also suggest my own notes, since of course, I will give my lectures according to my personal viewpoint, and this is reflected in my notes. So the notes may be found, these notes may be found from this. You
put a link on the school webpage
already? Yep, it's already there. Okay, so I will save the 2 seconds needed to write this. It's available from the school webpage. Okay, so perhaps we may start. No, concerning, by the way, I didn't give these 2 references concerning the last part, modular spaces. One good reference for the differential geometric approach is a book by Kobayashi, which is called Differential Geometry of Complex Vector Bundles. And a book by Ulbrecht and Lehn, which is called, I believe, again, this is much more algebraic, and it's possibly something like modular spaces of sheaves on surfaces. Okay, so perhaps we start. And well, actually, I sent a program for these 3 lectures, and the program contains really an awful lot of stuff. So I don't really know what I shall be really able to cover. I'll do my best. So we shall need, all through these lectures, we shall need some homological algebra. So I will start with I could call it a micro-pill of homological algebra. So we need to talk about exact sequences, homology, cohomology, so we need some basic terminology, some very basic tools. So the idea is that, well, what we need is to talk about modules over rings. So we shall consider what we need is a commutative ring with unit. At least at the beginning, there is no harm in thinking we are working with z, the integers, or with the complex numbers. And we shall consider modules over this fixed ring. And then we may have a first definition. We say that a pair MD is a differential module. A differential module is the basic object you need in order to do homology or cohomology. So the idea is that M is a module over R, and we have a map of M as a module over R. So we call this map M, with the property that this map squares to 0. And this map is usually called the differential, or the differential module. Since the map squares to 0, its image is contained in its kernel, and therefore we may take a quotient. And this is, well, at this point, actually to say homology or cohomology makes no difference. Let me call it cohomology. And we may denote it like this. We shall need to consider a situation where we have maps between differential modules. And then if we have two differential modules, say MD, therefore we have a map D from M to M, and ND prime, the very natural notion of homomorphism between these two objects is that we have a morphism between the modules, and this commutes with the differentials. So this is the notion of morphism of differential modules, and it's very easy to check. I will not do this. That this induces a morphism between the cohomology groups. Well, the objects that are in the kernel are usually called closed objects. The objects that are in the image of the differential are called exact objects. And then it's very easy to check that if f has this property, then it sends closed objects to closed objects and exact objects to exact objects. As a result, it defines a map between the cohomology groups. It's very easy to check. This map, usually called H of f. Well, of course, it would be very nice to give plenty of examples. We don't have that much time for doing that. Let me just mention that, for instance, it's very easy to build up examples by, if you already know this theory, by considering the Ram cohomology of a manifold. And then if you have a map from a manifold to another, it's easy to construct a map between the Ram cohomologies using this stuff. The map goes the opposite than the map between the differentiable manifolds, and exactly fits this structure. Okay, so this is the first notion, differential module, its cohomology, etc. And we shall also need the notion of an exact sequence of R modules. So suppose we have two maps between, so M prime, M double prime are R modules, and we have maps in this way. Then we say that this is exact if three conditions are satisfied, the first map is injective, the second map P is surjective, and the third condition is that the image of I coincides with the kernel of P as a submodulus of M. And this is usually understood by writing zeros on the two sides, because then injectivity of I means that its kernel is the image of 0, and surjectivity of P means that its co-kernel is 0. Anyway, this is just notation. The meaning of a sequence to be exact is these three conditions. An example, an interesting example, which will generate then a very interesting and useful example when we shall talk about sheaves, is the following. You may inject the integer numbers into the complex numbers, and you can compute the exponential of complex numbers. In particular, it's convenient to include here a factor of 2 pi I, and then this maps to the non-zero complex numbers. There's non-zero complex number, so in this case the ring is Z. And by the way, to be a Z module is the same thing as being an abelian group. The two notions are exactly the same. And C star, it's definitely an abelian group with its multiplicative structure. And then this X plays a morphism of abelian groups if in C you consider, as we very well know, in C you consider the additive structure, and C star you consider the multiplicative structure. Then usually one puts a 0 here, and then here depends how precise you want to be. Perhaps one should put 1, which is the neutral element in this group. Or you can write 0, whatever. So, simple instructive exercise, check that this is an exact sequence. Now, we put the two notions together, and an interesting situation arises when you have an exact sequence of differential modules. So this means that you have an exact sequence of modules. But in addition to this, every module has a differential, making it into a differential module. So you have a differential here, one in the middle and one on the right, making this diagram commutative. Okay? So not only we have an exact sequence of modules, but we also have differentials, and the differentials are compatible with the morphisms in the exact sequence. So we have this situation where the two rows are exact, and all squares in this diagram commute. And here, a very interesting feature arises, which is a very useful, also computational tool in homological algebra, which is the following. So let's call I and P as before the two morphisms. So I will understand the differential in this notation. So we have a morphism going to the cohomology of M. From here we have a morphism H of P going to the cohomology of M double prime. Now what happens? is that using basically this diagram, you can build a further morphism. So you may complete this to a triangle. There's a morphism here, which I will call partial, which not only makes this diagram commutative, but it also makes it exact. So this means that in this loop, so to say, the kernel of every arrow is equal to the image of the previous arrow. So this is what is called an exact triangle. And it's a not completely, I mean, it's a very easy check to, I mean, it's very easy to construct this, but it requires some lengthy checks. The idea is that you simply use this diagram. You start from an element in the cohomology of M double prime. So this psi is an element in a quotient, so you can represent it with some element in the module M double prime. And then what you do is you take this element, you take an inverse image here because P is surjective, you push it down, you realize that it lies in the kernel, and then it comes from M prime. And then you take its cohomology. It's simply like this. So the idea is that you do this. But then you have to make checks. For instance, you need to check that the cohomology class you get here does not depend on the choice of the counter image here, for instance. And a few more checks. But you can do that. Now, you might say that all this looks unfamiliar. Actually, what happens is that usually one sees all this in a situation where you have an additional structure. Namely, you have what is called a grading. So now we throw in a grading. So this means that, for instance, when we consider a differential module, we assume that actually M is a graded module. For instance, graded over the integers, namely it is direct sum of summands say labeled by the integers. And you also assume that the differential is of degree 1. In this moment, we are choosing homology as opposed to homology. Because if we were doing homology, the degree would be -1. Okay, so D is again a morphism which squares to 0, but additionally it is of degree 1. It increases the degree by 1. As a result, also the cohomology group is graded. So it is a sum, a direct sum of cohomology groups, each given by a choice of the integer. Now, very little changes here. In particular, if we consider this situation, I mean exact sequence of differential modules, it's very easy to check that the two morphisms that the two cohomology morphisms that we associate with I and P have this are of degree 0. But the morphism delta, let's give it its name, it's called the connecting morphism, is of degree +1. So this means that if you start from Hn of m double prime, you get to Hn +1 of m prime. And this is very easy to understand because in our definition, there is one point where you apply d here. You remember that the idea was to go this way. P and I have degree 0, so the degree doesn't change. But when you apply d, you increase the degree by 1. So for this reason, the connecting morphism is of degree 1. It behaves like this. The result is that the triangle, in some sense, opens. You may write it as a linear object. And in particular, very often, the grading is over the natural numbers, which means that we can make, very often, we can make the assumption that the summand of negative degree of the complex are 0. I said complex because an object like this, it's usually called a complex. Of R modules. So if this is the case, we can, if we want to write now the triangle, remembering the degrees, we may start from H0 of m prime. There is nothing before this. So before this we have 0. And then we know we have a map to H0 of m. We know we have a map to H0 of m double prime. And then we have the first connecting morphism going to H1 of m prime. And then again we have H1 of m and H1 of m double prime. These maps are, of course, H of I and H of P. And then here again, we have a connecting morphism going to H2 of m prime, etc. Okay, and then this long exact sequence, this is called, an exact sequence. I call this an exact sequence altogether, but if you want to be more precise, an exact sequence with 3 terms is called a short exact sequence. You may very well have exact sequences with more terms, always with this condition that the kernel of an arrow equals the image of the previous arrow. And in particular, we see that when we have an exact sequence, we could say in this case of complexes, there is an induced long exact sequence in cohomology. This may be infinite, also on this side, by the way. Just I chose to consider the case of natural numbers just because it's what most often happens. It can also terminate. That depends on the situation you are considering. Yes, please.
What again was the reason why you consider homology as a covariant functor? So the arrows have to change in homology.
At some point I decided to consider cohomology. Had I decided to tell you about homology, this differential would have degree -1, so going to mn -1, and this the arrows would be the other way, so decreasing the degree. So the connecting morphism would decrease the degree by 1. And then it depends. You may have a cohomology complex or homology complex. This is an input datum now.
I guess by definition, cohomology is contravariant. So
No. There's nothing to change here. We are not applying any functor. I understand what you have in mind. And this is, or perhaps I will spend, this is a kind of an example. So, provided you know something about differential forms. So, let me say this is an example. You have a manifold, X, differentiable manifold. Okay, and then you consider the differential forms with a Cartan differential. Okay, sorry. So this is a complex, the RAM complex of X, because D squares to 0, and you have a cohomology. So the cohomology is some name, we may denote it like this, where K goes from 0 to the dimension of X. What you are referring is the following, I guess, that if you have a morphism between two differentiable manifolds, then you have an induced morphism between the complexes, which goes the opposite way. And this is an example of a morphism, since this commutes with D. It's an example of a morphism of complexes. In this sense, the RAM cohomology as a functor from the category of differentiable manifold to the category of complexes is a contravariant functor. But I was not talking about this. I already had a complex. You see that what happens here is that already the map between the complexes go the other way. So it's another, it's a more articulated situation with more stuff in it. Okay. Okay, not bad. So this is the end of the pill.
There's also a bigger eraser.
Yeah, but this needs water. I prefer this. I'm sorry. It works reasonably well. Okay. So next, so this is, so to say, the end of the first part of this lecture. Now we go to sheaves. This is the second topic of this lecture. Actually, we start with pre-sheaves. Let me say that one can consider pre-sheaves of more or less any kind of algebraic structure. So we may consider sheaf of abelian groups, sheaf of rings, sheaf of algebras, sheaves of whatever. Let's fix our attention to sheaves of abelian groups. Okay, which, let me recall, it also means Z modules. Okay, a Z module is exactly the same as an abelian group. So the idea is that we start from a topological space. Well, there's a more rigorous way to say what a presheaf is. So what am I going to say is a little bit, how to say, it's a little bit rough. But anyway, it gives the idea. Otherwise, you can give a more refined definition saying that a presheaf is a functor, but really it's not needed. So the idea is that, and this is the weak point, the sentence that I'm going to say, the weak point of the definition, a presheaf is the assignment to an abelian group to any open set in the topological space. So I will denote by P a presheaf. The idea is that whenever you have U, which is an open in X, to this you associate an abelian group that I will call P of U. But we want that this assignment satisfies some locality property. So in some sense, the assignment that we make on different open sets should be compatible. In particular, it should be compatible with the inclusion of open sets. So in other terms, whenever we have an open set which sits inside another, therefore we have the group P of U and the group P of V, we want that there is a morphism between the two that we call, for the moment, rho UV, which in some sense, it is called the restriction morphism. From the moment this, at the moment, this is just a name. Okay, it's called restriction morphism. Then, of course, in the example that we are going to make in a moment, this will be a true restriction morphism. But we want more compatibility conditions. In particular, we want the following. Suppose you have 3 nested open sets. Of course, W is also an opening U. So in order to go from U to W, there are 2 different ways. And you want these 2 ways to give the same result. Okay? So we have this additional property. The first property is that we want that the restriction morphism exists. The second property is that they satisfy this commutativity. And the third condition, which is needed in the case of pre-sheaves, is that there is a very particular open subset, which is the empty set, and to this you want to associate the trivial abelian group. Okay, so this is a pre-sheaf. Of course, we have plenty of examples of pre-sheaves, and perhaps the most natural that you have when you consider a topological space is the pre-sheaf of continuous functions. So to every open set in our topological space, you associate the continuous function from that open set to the real numbers, for instance. Okay, so X as a topological space knows about continuous functions. And so you consider the continuous functions from that open set to R. And you can immediately understand that the 2 conditions, of course, the restriction maps, the restriction morphism will be exactly the restrictions of functions. If you have a function on U and V subset, we may restrict. And of course, the restriction functions satisfy this condition. Okay? So this is one example. You can even make much more trivial examples. For instance, you could do the following. To every non-empty open subset, you associate the same group. For instance, the real numbers. And the restriction morphisms are always the identity. This is a very trivial example, but still it has something in it, some non-trivial thing in it. Next step, now we say what a sheaf is. As the name says, pre-sheaf is an intermediate notion we want to improve to get to the notion of a sheaf. And indeed, a pre-sheaf is a sheaf which satisfies 2 additional conditions, usually called the sheaf axioms. And the sheaf axioms are, the first is a locality axioms. You see, the sheaf axioms, in some sense, just state that a sheaf is a pre-sheaf given by local data. So the specification of a sheaf must be a local specification, in the sense given in a precise way by the axioms, of course, that we are going to see. The first axiom says that, so I should add something about the terminology. The elements in P, if you have a pre-sheaf, the elements in the group we associate to an open set are called sections. So the idea is that a section is zero if it is zero locally, which means the following. This is a little cumbersome to write. For every open set in X, every section of a sheaf that we call F, standard notation, of course it comes from French. Or, well, of course I don't know why, because in other languages sheaf starts with F, but in particular sheaves were invented by Jean Leray, as far as I know, so we owe this French terminology to him. So for every section in our sheaf to be over U, and every open cover Vi of U, if the restriction of S, let me denote it like this, to any Vi 0, then S is 0. So in order to check that a section is 0, it's enough to check it on the open covers, on the elements of some open cover. So in this sense, it's enough to check it, to check this locally. So this is the first axiom. Again, you see that immediately we realize that our pre-sheaf of continuous functions satisfy this condition. Correct? Because if a function is 0 in an open cover of something, is 0 on that something. It's a trivial statement. Also, the second pre-sheaf satisfies this condition. Since the restriction morphism at the identity, if you get 0, it means that you have 0. So this, even the second stupid pre-sheaf satisfies this locality axiom. So here, we started from U, we had an open cover, and realized that, or we stated, assume that it's enough to check the vanishing of the section on the open sets in the cover. The second axiom is the so-called gluing axiom, which states that you may build up a sheaf or a section of a sheaf by gluing local sections, satisfying some conditions, of course. Of course, we don't want to be able, we don't pretend to be able to glue anything. So the idea is the following. For every U, again an open subset, and any open cover Vi of U, let Si be sections over this Vi. So on any of these open sets, we assume we have a section. But then we assume that on the possible overlaps, these sections coincide, such that S restricted to Si, restricted to intersection Vi intersected with Vj equals, this is an I, Sj restricted to this, provided, of course, that the intersection is not empty. Then the idea is that we have a section, global section over U, which restricts to the given Si.
Sorry, this restriction is just the image of the restriction morphism.
Yeah. Yeah, at some point I introduced a quicker notation, so this I denoted, for instance, like this. Then there is a section over U such that it restricts to the given SIs. So section may be glued provided they satisfy a gluing condition. It may be seems to be stupid, but I invite you to check that the second preshave we introduced does not satisfy this condition. While the first does. Again, it's a matter perhaps of triviality in the sense that this is the way in which very often we define functions. We define on some open cover and we check that on the overlaps everything is okay. And then we assume that this is defined globally. Right? This is what we do in everyday life very often. So we are using the fact that, say, continuous functions are a sheaf. But it's very easy, as we did, to introduce an example, of a presheaf which is not a sheaf. This presheaf only satisfies the first axiom. Note was forgetting to say that this section that we assume to exist will be unique if the first axiom is satisfied. Okay, but so if the two axioms are both satisfied, then in the second we can forget about uniqueness because it's given by the first. It's a simple exercise should show you that this is indeed the case. So you see that, of course, this is a slogan, but these two axioms justify the saying that a sheaf is a presheaf given by local conditions. So we may very well think that all objects that we use very often in our daily practice are sheaves, but sometimes they are not. Another example, which I leave you to your consideration, provided, of course, you know some differential geometry. But I guess I can assume that this is true. Again, suppose that we have a differentiable manifold. And then we fix a K, and to every open set we associate the K forms. Okay? On every open set we consider the differential K forms on it. I claim that this is a sheaf. Okay, this I claim, I leave it to you to show it. By the way, the fact that this is satisfy the sheaf axioms basically follows from the fact that you may use on a differentiable manifold local coordinates, and then a differential form, it's at least locally given by a bunch of functions. C-infinity functions, but of course I'm assuming that we already know that C-infinity functions are a sheaf. Okay, so on X, if you want, we have a first example. The C-infinity functions, the differentiable functions, make up a sheaf. And I say that also the differential forms make up a sheaf. Now we may consider two kinds of differential forms. The first is the closed differential forms. So you consider for every open set the Cartan differential, and you consider the kernel of this. Okay? These are the closed forms. And I claim that this is a sheaf. This gives rise to a sheaf. Why? The idea is that, well, actually there is no problem for the gluing axiom, because after all, closed forms are forms. But in particular, the locality axiom is satisfied because in order to check whether a form is closed, it's enough to do it locally. Being closed is a local matter. Okay? A form is closed if it is in the neighborhood of every point, so to say. So this is the reason why this is a sheaf. On the other hand, you may consider the image. So what is called the exact forms. So the image of D going from the k minus 1 forms to the k forms. And I claim that this is not a sheaf. Actually, as we know, if we know something about the rank homology, Poincaré lemma, etc., the fact of being exact is not a local issue. Okay? And again, I leave this to your meditation. But if you meditate enough, you should come to the conclusion that the exact forms don't make up a sheaf. There's a part of the story which I don't have time to tell you, which says that if you have a pre-sheaf, there is a canonical way of making a sheaf out of it. So there is a way of a sheafify, so to say, a pre-sheaf. There is a canonical way. And it's not surprising that if we apply this technique to the sheaf of exact forms, we get the closed forms. By Poincaré lemma, we basically know that locally exact forms and closed forms are the same thing if we are on an open set with a nice shape. So it's not surprising that if we apply this technique, we get that. I mean, from exact forms, we get closed forms. And we could think of applying that technique also to our constant pre-sheaf. And in that way, one can show that we get something different, but by construction is a sheaf. So we get what is called a local sheaf. Unfortunately, I don't have time to go through these details. By the way, as an additional reference, of course, you can find this, for instance, in my notes, but an additional standard reference is the book by Godman, for which I don't know if an English translation exists. I'm accustomed to use the French original, and you can find very detailed discussions of all this stuff. Okay. Okay, so this is the end of the second part. Now we know about sheaves. Okay, so the idea is to stop around 12:20, so we have some 10 minutes for questions. Okay, we are quite in good shape. And the third part of this lecture in some sense, puts the two previous parts together. And the idea is to introduce some homology theory that we may associate with the sheaf. And in particular, we are going to consider check homology. So we have a topological space. The idea is that we have a topological space and a sheaf on it. Well, actually, it could, to start with, maybe a pre-sheaf. But to start with, to define check homology, we need something more. We also need an open cover of the topological space. So U, this pretends to be perhaps a Gothic U or something like that. That's my notation for open covers. So this will be something like this. So we have an open cover which is labeled by some index set, and we assume this is to be ordered. Totally ordered. And then to define a cohomology, we know we needed to define a complex. And let me define the few terms. This complex will be labeled by the natural numbers. And let me define explicitly the first few terms. So the first, so we have this rather Baroque notation. An element here, which will be called the zero cochain, is the specification of a section for every open set there. So an element here, say alpha, will be a collection alpha I, where each alpha I is a section over ui. Okay, so we have a section on any open set. This will be a zero cochain. So if we want to be more formal, this group is the direct product over all labels of the groups P of ui. Okay? Which means exactly this. We have a collection like this. Now, the idea is that we do the same for every possible, for intersection of every possible order. So next step, we shall do the same for double intersections. So perhaps I will introduce a notation. For the moment, I will denote by uij the intersection of ui and ij, provided this is different from the MP set. And C1 UP will be the direct product over all pairs I and j, where to avoid overcounting, I assume that I and j are always ordered, I is less than j, of P iuj. And we go on. So now it's not difficult to realize what I should write if I want to consider P cochains. We shall have a direct product over all collections over all ordered collections of P plus 1 indices of the groups corresponding to the given intersection. Now, for instance, we go back to one cochains. We can write something very explicit again. And one cochain is a collection of sections here. Okay? So on every double intersection, we have a section. Now it's easy. Well, at this point, it's not difficult to... We need a differential now, right? We have just defined groups. These are abelian groups. We need a differential. Namely, we need something which goes from p cochains to p plus 1 cochains and squares to 0. Then, for instance, it's very easy to define the differential here. I will call it delta this way. If we start from an object like this, now this needs to have a collection, two indices, because it's going to be a one cochain, correct? So we need to specify something with two indices here. And the idea is that, of course, it should be defined, this cochain should be defined on every intersection. And so the idea is that we compute restrictions. So this will be alpha j restricted to the intersection minus alpha I restricted to the intersection. As you see, this makes very good sense and produces exactly what we need. This is a one cochain. Let me be a little pedantic, but just to give some idea, let me do by hand also the next step, and we check that we get the delta squares to 0 in this case. And then we define it in general. So the idea now, if we have a one cochain like this, and we want to apply delta, now this will have three indices. While beta is just 2, but the idea is that you omit the three indices in succession with a sign. So this will be beta jk restricted to the triple intersection minus beta ik restricted to the triple intersection plus beta ij restricted to the triple intersection. Perhaps I will go there. Now, what if compute this? So the idea is that so delta alpha is up there. So we need to write alpha j minus alpha k. And then we need to write minus alpha I plus alpha k. And then we need to write plus alpha I minus alpha j. All these are restricted to the triple intersection. And you see that we get 0. Okay. So this means that we are in business. And we can write a general formula. If alpha is an element in C P, if alpha is a P cochain, then delta alpha will have P plus 2 indices and will be the sum minus 1 to k going from 0 to p plus 2 minus 1 to power k alpha, where you omit the kth index, here p plus 1, yeah? Sorry, 1 too much. So this is the general formula. You see it's exactly the same. You omit in turn an index, you have an alternating sign, and you restrict to the relevant intersection. And exactly for the same reason, it's very easy to write it. If you compute the square, you always get 0 because you write twice the same object but with a different sign here by making a relabeling. So we are in business. We have a cohomology complex. So we can take homology. And we get these groups for every k. So for the moment, these groups depend on a triple: the manifold, the sheaf, the pre-sheaf, and the open cover. We might think that it's a little bit inconvenient to have the open cover. Really, it is not, because this is what makes check cohomology very computable. Because you can make a computation using open covers. But perhaps at least at the level of definition, you would like to have something which is independent on the open cover. Then one has a rather tricky situation in which, on one hand, you dispose of the cover. How? There's a general procedure in homological algebra where you can consider a limit, for instance, of these groups when you take open cover that are finer and finer. So if you have an open cover, you have a notion of refinement. It's another open cover whose open sets are subsets of the open sets of the previous cover. So the open sets are smaller, so to say. So you have a notion of refinement. It's possible to show that when you have a refinement of an open cover, you have a map between the cohomology groups. And this is exactly an example of what I did. I mean, morphism of complexes and induced morphism in cohomology. And this allows one to take a limit, which is called an inductive limit, but I will not go into the details of this. But the idea is that out of this, you may consider groups which will depend on X. Here, to avoid confusions, one put check stress on the H. But now the price that we pay is that there is no way of computing this. This is an abstract object. And then what one does usually is to consider a situation where actually you consider open covers which exactly compute the limit. So there are open covers for which the cohomology coincides with the limit. And then it's very good to consider such open covers. So this may be rather, all this definitely sounds very metaphysical, but of course there's a question of lack of time. Let me suggest a very easy exercise, but you know, easy exercises very often are important to understand what one is doing. So we consider S1. On S1 we consider the constant sheaf we defined, and I propose you to consider this open cover. So an open cover made by 3 intervals, which have the very nice property that they overlap on connected intervals, I mean subsets. the exercise is compute the cohomology of this open cover. And the exercise will show that what you get is the same as the Ram cohomology, if you know the Ram cohomology. And of course, the result is by no means occasional. I mean, of course, there's a reason for this. But anyway. Now, time is flying. So let me spend the last 10 minutes in discussing a situation where long exact sequences in check homology arise. Unfortunately, this requires a little discussion on the notion of exactness that we use for sequences of sheaf morphisms. I'm cheating actually because I never introduced the notion of sheaf morphism. Or preshave morphism. So let's first introduce that. A preshave morphism from P to Q, so P and Q are two presheaves on the same topological space. This is simply a collection of morphisms between the corresponding groups. Right? For every U, we have two groups, P, U, and Q, U, and so we want to have a morphism between the two. Of course, we don't want this to be just independent of the presheaf structure. And then we want this to be compatible with restrictions. So if we consider a subset, we shall have another morphism FV. Vertically, we have the two restriction morphisms. I use the same letters, but actually they are restriction morphisms of different presheaves, and you want this to commute. Right? Otherwise, we are in serious trouble. So this is a notion of a morphism of presheaves, and for sheaves, you use the same notion. Now, the road is open to consider exact sequences of presheaves, because we are very clever, and we say, very simple, if we have two morphisms of presheaves, say I and P, we say that this is an exact sequence if it is so on every open subset. So for every open subset, we have a sequence of morphisms. And we ask this to be exact for every open set U. This is very good. It makes a very good definition, but unluckily, the exact sequences of presheaves are exceedingly rare. So it is too strong a requirement. And it's very easy, for instance, to make an example. Suppose you remember this exact sequence. Out of this, we can use this as a suggestion to get an exact sequence, whose blocks are sheaves. So we consider, for instance, suppose that X, can I say X is a complex manifold? We know more or less what a complex manifold is, right? Anyway, I'll give this definition in the next lecture. So X is a complex manifold. Z is the constant sheaf on it. And now instead of C, I consider the sheaf of holomorphic functions. Yes, please.
Concerning, excuse me for being late, but concerning the preshave morphism, are you requiring that the morphism of abelian groups PU and PV, between PU and PV and QU and QV, are you requiring to be the same, or just applying the notion of natural transformation?
Natural transformation. You are using the term natural transformation in a categorical way. Then, exactly, if we say that a preshave is a functor, which it is, it's a functor from the category of open subset of topological spaces of from the beginning. So X is a topological space, and you may consider the category of its open subsets. The morphisms are the inclusions. And then a preshave is a functor from, is a contravariant functor from this category to the category of abelian groups.
Yes.
Then the morphisms are the natural transformations.
Yes.
That's it.
Yeah, that's fine, but I mean,
And this is exactly this.
yeah, but aren't the rows are the same?
Huh?
The question.
No. I just said that I'm using it. It's an abuse of notation.
Okay, then sorry.
Yeah, I should. It was I consider this to be a little too baroque to use, but it's no. Of course, they are different morphisms. So here we consider the holomorphic functions, and then we consider the holomorphic functions which are never zero. Holomorphic functions without zeros. This is the just inclusion. A section of this constant sheaf is just an integer number, at least on a connected set. In particular, a constant integer number is a holomorphic function, of course. So we have inclusion, and here is the same exponential as before. Now, this is not exact in the sense of presheaves, because, for instance, if you take this example where X is just the complex numbers, so the base manifold is the complex numbers, and we consider the open subset that we obtain by removing the zero, and we consider the section Z meaning the standard coordinate on C. This is not in the image of the exponential because of the usual problem with the logarithm, which is multi-valued. So Z is not in the image. The problem is that our open set includes 0. But anyway, this means that this map is not surjective for all open subsets. It becomes immediately subjective if we consider a contractible open set, basically. So if U is contractible, in this case, I mean, then exp from OX of U to OX star of U is surjective. So we see that it's not true that this is an exact sequence of presheaves. But then what we do is to change the definition. Now I'm a little bit in lack of terminology, but the idea is that we require, we give a new definition, and we say that this is exact in the sense of sheaves when the last arrow is locally surjective. So every point has a neighborhood over which the arrow is surjective. This is not exactly the top in terms of elegance, but it makes the job. Okay, in order to say this in a nice way, I should introduce the notion of stalk of a sheaf. But I don't have time to do that. Anyway, the idea is that we require exactness only locally. And when this is true, when the exactness holds locally, we say that a sequence of sheaves is exact. And in particular, this becomes an exact sequence of sheaves. It's an example of an exact sequence of sheaves. Now, what happens? We would like the following. Suppose we have one can prove the following theorem. If I think I will stop. Then I'm almost at the end, but I'd like to have some time for questions. So we have time this afternoon to finish this. So suppose this is exact as pre-Sheaves. Then one can show that we have a long exact sequence in check cohomology. Now, this is very long to write.
You mean exact as Sheaves?
No, pre-Sheaves. Otherwise, this is in general wrong because I'm not assuming anything on X.
You also assume the same thing that you just explained. So it's only
No,
exact on the start.
no. I'm assuming that as pre-Sheaves means for every open set. This is a very strong condition. On every open set, the sequence is exact. Then we get this. Well, I should prove this, okay, but so here we have a connecting morphism. The fact is that from this we get an exact sequence of complexes, and from this we get this. But this is exactly the problem, that usually our sequences are exact only as a Sheaves. So under this assumption, in general, this theorem is wrong. It's not true that we have a long exact sequence. Thank you. Yeah, prime here. So the point is, can we consider some situations where nevertheless this is true? So we assume that the sequence is exact in the sense of Sheaves, and we have nevertheless a long exact sequence of cohomology. Now it turns out that there are two situations. Luckily enough, one is what happens in differential geometry, and the other is what happens in algebraic geometry, in some sense. So for today, I don't have time to say more, but one can say the following. If you have an exact sequence of Sheaves and we are on a topological space which is paracompact, I will say what it is in a moment, then the same. So the paracompactness of the space comes to our rescue and allows us to write a long exact sequence of cohomology anyway. A space is paracompact when it is Hausdorff and every open cover as a locally finite refinement. So you can consider covers such that you have a point at the neighborhood and a set in this cover, then only a finite number of other sets will intersect this. So you can consider open covers in which the sets, so to say, intersect only finite many of them intersect. You don't have infinite intersections. When this is true, then you can prove that starting from an exact sequence, for instance, like this, you have a long exact sequence in cohomology. Unfortunately, this is not what we need in algebraic geometry, because as we shall see this afternoon, in algebraic homology, one doesn't use, for instance, if on this space C, we think the analytic topology, so the topology that has as R2 with the standard topology, then this is paracompact, we are in business. But this is not the topology that one uses in algebraic geometry. In algebraic geometry, one uses another topology, which is called the Zariski topology, which doesn't satisfy this condition. But in that case, it works anyway for other reasons. And I will give a hint to that this afternoon. Now I guess it's high time for me to stop. Time for questions, I guess.
Please repeat the definition. Could you please repeat the definition of
They want the categorical definition of presheaves.
Yes.
Because then, in any case, as far as I know, a sheaf is a presheaf which satisfies the sheaf axioms, the two axioms. Yeah, sure. So the idea is the following. So we have a topological space, and from this we consider a category open X, whose objects are the open subsets. And the morphisms are inclusions. Okay, I only consider the inclusions. This is a well-behaved category. And then another category I consider is the category of abelian groups. Objects are the abelian groups, and the morphisms are morphisms of abelian groups. And then I claim that a presheaf is a functor, a contravariate functor between these categories, with additional assumption that P of the open of the empty set is the trivial group. So this means, as we know, that to every object here we associate, to every open subset we associate an abelian group, as we said. This is what avoids one to use the terminology an assignment which is not so nice. And to every morphism, which is an inclusion, associates a morphism between the corresponding abelian groups, which goes in the reverse way, because the factor is contravariate. So, if V is in U, which means that there is a morphism in this category, we want to have a morphism between the corresponding groups the opposite way. Okay, so this is a contravariate factor. And I mean, this is just, for the moment, it doesn't add anything to what we said, just a nicer way of saying what a presheaf is.